physics B6 Ohm's law. Okay, if we have Ohm's law, well, Ohm's law in a circuit, it shows us the relationship between current I, voltage V, also called potential divider, and resistance R. So between Ohm's law is current, voltage, resistance. Well, the formula that links all of them together is current equals voltage over resistance, or variations of this formula. If you do the triangle, you're going to have voltage, you're going to have current, and you're going to have the resistance on the bottom. Okay, now let's see how we mathematically we know how to solve this. Let's see how we're going to graph this situation. So we have an experiment. We're looking at the relationship between current and voltage. Now we have two options here. I'm going to look to plot current on the x-axis and voltage on the y-axis. Well, I'm going to plot I'm going to plot current on the y-axis. I'm going to plot voltage on the x-axis. What is the difference? Well, let's look at the gradient. So you have a gradient, which at this moment we say it is a straight line. If it's a straight line, it means that this law, Ohm's law, is followed. That means we see here we have direct relationships or invertible straight line relationships, let's put it this way, between voltage and current. Okay, so let's say the first graph, where the gradient, which is the line, this is the line is the gradient, is equal with y over x. Now y over x is voltage over current. Now if I look at my equation, if I say, okay, I equals V over R, that means R equals V over I. This is y over x in my case. That means this gradient will be equal with R. But if I'm looking at the bottom graph, where the gradient is always y over x, so it's going to be y over x, but in this situation is I over V. Now if I get the same equation again, current equals voltage over resistance, then I will say, okay, resistance equals voltage over current. But you see, our graph gives us current over voltage. That means this gradient is not going to be R like the one on top. It's going to be 1 over R. That is the difference between one and another. These are called ohmic devices. That means they follow Ohm's law. So you're going to get gradient, a straight line that's going to go through the origin. Now let's look at some graphs that do not follow Ohm's law. So if I have a filament bulb, wire bulb, the one that's the traditional, the old one, let's put them like this, and then this is current and this is voltage, and you see the bottom diagram, I made it a bit differently. This is going to be a diode. These two are called non-ohmic devices, and then because they do not follow Ohm's law. What does it mean? Well, I equals V over R, this is a direct relationship, is not followed in this situation. Now if I have a filament bulb, if I have current over voltage, my graph will be, my gradient will be a curved line. So obviously if I use the tangent, I can calculate the resistance at any point. So I can calculate an instantaneous resistance, but I cannot calculate an average resistance as I did previously. A diode, on the other hand, we're going to talk about this more on the next diagram, has two possibilities. One is called forward, one is called reverse. If you look at this graph, you see that if the current is moving in one way, we call that reverse. There is no current. There is no current going into the circuit, because in reverse a diode has a very high resistance, and we know that high resistance means low current. But this is so low in this instance that there is actually zero current there. In the other situation, when the current is moving in the other direction, forward, now you see here, if we discuss already about current going forward and backward, that will be AC current, alternative current. Now, when it's moving forward, once it reaches a point, usually 0.6, 0.7 volts, threshold point, the current starts flowing through. So here the resistance will be low when the voltage is 0.6, 0.7 volts, and current starts flowing to the diode. But again, we see we're not talking about straight lines here. That's why these devices are called non-ohmic devices, because they do not actually follow this Ohm's law properly.